Good morning. So here we are at an AI conference with someone talking about quantum computing. People usually say I'm an original, so I guess that's true. But please bear with me because I know exactly what I'm doing, and there's a very good reason why I want you all to hear what I have to say this morning. So I love a good story, so I will start with one. This happens in the 90s. A young engineer, the founder of a new company, small startup nobody has ever heard of, is working on self-soldering computer parts. His dream is to revolutionize the video game industry. And so they keep working, he and his team. Soon enough, they land very large contracts from video game companies. You'd think they made it, but the reality is there's always ups and downs in startups. They realized that what they were building was not quite what their customers were expecting. And so they're almost on the brink of bankruptcy. Luckily, something amazing happens. One of their customers decides to give them a lifeline. Not only they don't drop the contract, but they decide to help them. Thanks to this, the company makes it, and a few years later, they become a leader in the video game industry. People fight to get their chips. Amazing success story, correct? Well, not so fast, because many entrepreneurs tend to be unhappy with what they have. They're very ambitious people, right? So this same person realizes quickly that what the technology is really good at is powering AI workflows. You might have guessed by now that the person I'm talking about is Jensen Huang, founder and CEO of NVIDIA, which is indeed powering all AI workflows this day, right? So the lesson here is that innovation can come from any places. Who would have thought when NVIDIA was started that eventually they would make such a big difference for AI? The story doesn't end here, right? So we're in 2025, first quarter of this year. Jensen is giving an update about NVIDIA, and he's being asked by a journalist when he believes the first useful quantum computer is going to come out. I don't know if you heard, but basically Jensen answered that the first useful quantum computer is 30 years away. And as a result, the stock market crashes, many people lose money. Unfortunately, I was part of them, but I have recovered by now, don't worry about me. Right? But the reality is, like, even the biggest innovators can make mistakes and realize that, or not realize something's coming, right? In Jensen's case, a few weeks after this happened, he actually called for a new workshop as part of one of his conferences, NVIDIA Quantum Day, and he actually starts hiring quantum computing experts. So, I guess we'll see what happens in the future, right? But this also calls for the question, where is quantum at today? What is true, what is not true? Because you hear different things from different people. After this happened, the CEOs of the biggest quantum computing companies basically challenged Jensen on his claims, right? Well, the reality is sort of mixed, right? Basically you don't have right now quantum computers that can run or train sophisticated LLMs. Most people don't know, but quantum computing was actually promoted and invented or proposed by Richard Feynman, the famous particle physicist, because he was very frustrated that he couldn't run quantum simulations and evaluate quantum processes with regular computers. So he was asking to create a quantum computer, and he's the one who actually started this, right? So no surprise now, the first use cases you see in quantum computers are around quantum chemistry, for example, right? On things that do involve material science, et cetera, right? So it's getting there, right? Basically you do have some really profound like innovation coming. It's not everywhere. It's not for every single use case, obviously, right? As I said before, basically, like, don't expect a quantum computer to be used anytime soon for training an LLM, but this is not all there is to AI today. And so we believe that in the next few years, like in the very short future, there will be like more and more like tangible applications for cases where you do need fast inference, and potentially see that in more and more places. So it's not as dire as Jensen seemed to believe like just a few months back, right? So why does it matter for AI? It matters for AI because quantum computers are particularly good at a couple of things. They're very good at search and optimization. If you have to explore a feature space very quickly, you would want to use a quantum computer because they can go very fast here. They can perform like very, very fast operations for routing, scheduling, these sort of things, right? I mean, and so it's already being used in this sort of applications. It's extremely fast at inferencing. So if you need to like quickly identify if there is fraud, or like basically like in the finance industry for recommendation system, it's already usable today. It's also very good at simulation, so it's very important for AI for science, for physics, like physics research and chemistry research. And this is a field that's growing fast these days, so I think it's important to consider that. So now I'm going to take a step back and talk about another problem most people don't realize, right? Before we got there with AI, things went pretty bad, right? I mean, basically, like we had like AI winters, one after the other, for over like almost like a century now, right? I mean, so it's not all rosy and shiny. We didn't get there easily, right? And the problem was never the research. The research was there very early. There was a ton of like really good work like that already happened like in the 70s for computer vision, and was only adopted much, much later, right? My theory of what this happens is basically like you'll see in a minute actually. So basically, like I'll give you my own like failure modes as somebody who's worked in data and AI for a while, right? So for better or for worse, one of my first jobs was working for Walmart Labs in e-commerce, right? I've seen horror stories here you wouldn't even imagine, right? I mean, so basically you have the first like typical problem where when you do recommendations that scale on a Black Friday, because this is something where you need like models to be retrained on a regular basis, you would expect like seasonal patterns, so there's no way you can actually like do the right recommendations without shipping a new model just before Black Friday. No way to roll back. So basically, like you have a problem and nobody has like basically all of the parameters get erased. It's very complicated to go back to the prior version, right? I mean, so no versioning and whatnot, right? Another big problem I've seen is basically like problems with finding the right data. So one of my responsibilities for the company was to source data for the teams I was in charge of, right? And at some point, I set myself to find a pricing index that we could use on search, right? Went around the company, found countless teams working on pricing, found a team that was expert, like especially built for pricing, right? They didn't even know who was using their pricing data. They had no way to track who to warn if something did go wrong, right? Eventually, this was a problem across the entire company. Walmart hired a consultant to look for problematic like areas, right? I mean, and basically, like we found that for basically inventory management, there were 27 different teams producing the same data, not talking to one another, right? And so this eventually led to using feature stores, right? So as you might see by now, again, the problem is not the algorithm, it's not the research, it's not, like basically the capability of what we can build, right? The problem is the operations around it, the engineering that supports, that serves as the backbone for building, shipping, maintaining AI systems, right? And so the same exact problem is starting to reproduce for quantum computing and for the usage of quantum computers for AI. Right now, there is no interoperability across different like quantum computers. So basically, like if you would want to deploy the same algorithm in several different places, you would have to rebuild everything from scratch. Observability is not there, right? I mean, basically, like there is no system where you can track what's going on, and so all of those things are things that are going to have to be developed in the next few years, right? So what MLOps did for ML enable like AI and make it cheaper, make it accessible, improving return on investment, needs to happen for quantum AI as well, right? I mean, and so again, we're pretty far there, right? So are we completely in the dark? Thank goodness we're not. There are lots of like communities, and there is a lot of like open source projects trying to provide like frameworks and tools for quantum AI, right? The problem is not so much the tooling. It's basically like making the tooling like easier to use for obvious reasons, right? But it's more specifically, it's the connecting tissue between these different pieces. Those are built by different groups, different companies that typically don't talk to each other. So we are in the exact same situation as the AI industry or the ML industry before somebody took the initiative to, for example, like develop Airflow, right? I mean, or look at containerization, right? This needs to happen now, right? So we believe that, like basically, like the good news is like we already sort of have a map of how to get there because we've done this before to some extent because we had to build like the operations to support AI, but there is still a lot more work to be done in the context of quantum, right? And so I'm personally worried because there are additional challenges in the context of quantum. Why? Because we don't have a lot of experts that understand both AI and quantum computers, right? I mean, quantum computers are typically being built by physicists who have no idea like the sort of constraints or latency we're talking about, right? Interoperability is inexistent. Basically, like it's really hard to have like different quantum computers like generated by different companies like basically talk to one another. There is research, but there is little like effort in trying to like build a consistent ecosystem in the industry, right? And so I believe this is a place where the open source community has to make a difference because otherwise we will end up in the same situation than we were with AI a couple of years ago, right? I mean, so it's really important that we train people, that people think about what's coming next, right? I mean, basically identify those additional challenges, right? Another challenge for the development of quantum AI tooling, right? I mean, is basically like the fact we're gonna have to deal for the first time with hybrid workflows, right? I mean, nobody believes that quantum computers are going to do everything, right? I mean, basically, like, basically, like, we believe that quantum computers are particularly good at computation. For example, they're terrible for everything that's data management because it's very hard to have redundancy. You have like because you're operating with quantum mechanics, right? And basically, like you have like qubits that decay, that lose information, and basically, like it's most likely that we're going to have to use like the same typical tools for data management. So how are we going to do that in a hybrid way? What does it mean? What does interoperability mean in the context where you're going to have to deal with both quantum computers and classical computers? This is an open question. So what do we do now, right? I mean, I'm not asking everybody to rush out of this room and basically like go do research on, like quantum AI frameworks, what exists out there. Some of those frameworks are still being built as we speak, obviously, right? I mean, but my call to action here is like to take this seriously because it's coming. It's not 30 years away. It's definitely happening in the next couple of years. There are already existing applications today for a certain number of niche applications and not so niche applications because it is usable for fast inference, search, and the couple of use cases I mentioned earlier, right? What I think is important is to build a bridge across our communities, the people working on quantum computers and the people working in AI, right? And certainly the people working on ML ops, right? I mean, the operational side of machine learning. So thank you for listening to me. I'm Jennifer. I love to talk about topics that are cutting-edge, novel. Always happy to talk. And yeah, thank you.